In a previous video, we've talked about multiplying polynomials in general, but in this particular video, we're going to focus on special case polynomials. And to be specific, there are two special cases that we're going to focus on. The first one is going to be called difference of squares. And the second one is called a perfect square trinomial. It's important to be on the lookout for these two special cases because they factor in a particular way. For difference of squares, keep in mind that it's always going to look something like this, where you have some sort of perfect square taking away another perfect square, like x squared minus 9. It's literally a difference of squares. Difference of squares will always factor into the product of two binomials where we are adding their square roots and we are subtracting their square roots. On the other hand, perfect square trinomials look something like this. Notice how the first and third term are both perfect squares, and if you take the square root of both of those, then you would get x and 5, and you multiply them together to get 5x. If you double that, you're always going to get the middle term here of 10x. This is another special case because this will factor into the sum or difference of their square roots squared. We would literally have two identical binomials. Let's go ahead and practice multiplying special case polynomials. For number 1, we have the quantity of x plus 3 squared, so we're going to go ahead and expand this and write the quantity of x plus 3 times the quantity of x plus 3. If we then go ahead and start distributing, this x times x is going to be x squared. This x times this other 3 in this second binomial is going to be 3x. And then if we go ahead and multiply this 3 by this x, and this 3 by this 3, that's going to be another 3x, and then a 9 at the end. Notice here that we can go ahead and combine these middle two terms here. So this 3x and 3x are going to combine to make 6x. So the perfect square trinomial we end up here is going to be x squared plus 6x plus 9. And if you want a little shortcut, what you can do in the future is you can just go ahead and square this first term, and that's going to be this first term of the trinomial. You can square the second term in the binomial to get this term right over here. And if you go ahead and combine and multiply x times 3, that would be 3x. And double it, and that'll be the third term that is in the middle of 6x. For number 2, we have the quantity of 2x plus 5 squared. So I'm going to go ahead and expand this, and let's go ahead and distribute or FOIL it out. So we have the quantity of 2x plus 5 times the quantity of 2x plus 5. Let's go ahead and distribute this 2x to this 2x, and then this 2x to this 5 over here. So 2x times 2x is going to be 4x squared. Then 2x times 5 is going to be a positive 10x. Following, we have this 5 times this 2x, then this 5 times this 5 over here. So 5 times 2x is going to be another 10x, and then 5 times 5 is going to be 25. Notice we have some like terms in the middle, which will always happen with these perfect square trinomials. And so we have 4x squared, and then 10x plus 10x is going to equal 20x, and then we have this 25 at the end. Again, if you just go ahead and square 2x, you would get 4x squared. If you square 5, you do get this 25. And if you were to multiply these together, you would get 10x. And if you double 10x, you would get 20x, which is in the middle. For number 3, we have this quantity of x minus 5 squared. So I'm going to go ahead and write the quantity of x minus 5 times the quantity of x minus 5. And if we go ahead and distribute this x to this x over here, and then this x to this minus 5, x times x is going to be x squared, and then x times negative 5 is negative 5x. Following this negative 5 times x and this negative 5 times negative 5, the negative 5 times x is going to be negative 5x, and the negative 5 times negative 5 is going to be a positive 25. In the middle, we have these identical like terms, which is supposed to always happen with these. So we have x squared minus 10x plus 25. For number 4, we're going to expand this so we can go ahead and write the quantity of 6x minus 1 times the quantity of 6x minus 1. If we go ahead and distribute this 6x to both of these terms in the second binomial, 6x times 6x is going to equal 36x squared, and 6x times negative 1 is going to be negative 6x. Following, if you take this negative 1 multiplied by 6, that's going to be negative 6x. And negative 1 times negative 1 is also going to be positive 1. So we're going to have this negative 6x and then a positive 1. If we go ahead and combine this negative 6x and negative 6x in the middle, that's going to be negative 12x. So finally, we can write 36x squared minus 12x plus 1. So far, the first 4 examples are all perfect square trinomials. For number 5, this is the first time we have our difference of squares pattern. So I'm going to go ahead and just copy this down. So we have the quantity of x plus 4 times the quantity of x minus 4. So notice what happens with these difference of squares. It's a slightly different thing that's happening here. So the first is x times x, and then it's going to be x times negative 4. So x times x is going to equal x squared, and x times negative 4 is going to be negative 4x. Following, we're going to distribute this 4 to the x, and then this 4 to the negative 4. So 4 times x is going to be a positive 4x, and then 4 times negative 4 is going to be a negative 16. You can notice here that this negative 4x and positive 4x actually cancel each other out because they are opposites. And so we are left with this x squared minus 16, which is a difference of squares. For number 6, we have another difference of squares pattern, and we notice that because we have 2 binomials that are almost identical, we just have one sum and one difference, or one plus and one subtraction. So we're going to go ahead and distribute this x to here and this x to here to both locations. X times x is going to be x squared. X times 7 is going to be a positive 7x. Then it's the negative 7's turn, negative 7 times x and negative 7 times 7. So negative 7 times x is going to be a negative 7x, and negative 7 times a positive 7 is a negative 49. With these difference of square patterns, you're always going to notice that there's going to be 2 middle terms that are going to cancel out. That always happens, and you're left with a difference of squares. Let's check out a few more here. So for number 7, we have another set of difference of squares. So we have 3x plus 4 and 3x minus 4. So again, they are very close to being the same, but they are not. So that's how we know they're difference of squares, because we have 1 plus and 1 minus. We'll do 3x times 3x, then 3x times negative 4. So 3x times 3x is going to be 9x squared. And then 3x times negative 4 is going to be negative 12x. Then distributing the positive 4 to this 3x and the positive 4 to negative 4, 4 times 3x is going to be a positive 12x. And then 4 times negative 4 is going to be negative 16. These middle 2 terms, notice how they are opposite, so they will cancel each other out. So we're left with a difference of perfect squares. So we have 9x squared minus 16. For number 8, we have another set of difference of squares. We notice that right away because we have the 2x minus 5, but then we have a 2x plus 5. So hopefully you're getting used to this pattern a little bit. We'll start with this 2x multiplied by 2x, and then 2x multiplied by 5. So 2x times 2x, that's going to be 4x squared. Then 2x times 5 is going to be plus a 10x. Then moving on to this negative 5 times 2x, and negative 5 times positive 5. So negative 5 times positive 2x is going to be negative 10x. And a negative 5 times positive 5 is going to be a negative 25. If you look in the middle here, these two are opposite, so they will cancel each other out. They add to get 0. So we're left with this difference of squares of 4x squared minus 25. Let's try some more here. For number 9, we have the quantity of this 3x minus 5, and it is squared. So that means we have 2 of the same binomials. This is not a difference of squares. This is a perfect square trinomial. And so we'll go ahead and distribute 3x to the 3x, then 3x to the negative 5. So 3x times 3x is 9x squared. Then 3x times negative 5 is going to be negative 15x. Then negative 5 times positive 3, then negative 5 times negative 5. So negative 5 times positive 3 is going to be another negative 15x, or minus 15x. And then negative 5 times negative 5 is going to be a positive 25. This negative 15x and negative 15x, they're not opposites, so they don't cancel out. Rather, they will double because they are 2 of the same. So negative 15x and another negative 15x combine to make negative 30x. And then we have this plus 25. For number 10, notice how we don't have the same binomial. We have one that has 2x minus 7, and the other one is close, but it's a little different. It's 2x plus 7. That being said, we know this is going to be a difference of squares pattern. So we'll go ahead and distribute this, but instead of the middle 2 terms doubling, they should cancel out. So 2x times 2x is going to be 4x squared, and 2x times positive 7 is going to be a positive 14x. Then this negative 7 times 2x is going to be negative 14x, and negative 7 times positive 7 is going to be a negative 49, so I'm going to write negative 14x or minus 14x minus 49. Again, because this is a difference of squares, these should be opposites, and they are, and they will cancel each other out, and we're left with a difference of squares of 4x squared minus 49. For number 11, it looks like we have this problem that has two of the same binomials, so we can go ahead and check this out. We have the quantity of 3x plus 4 times the quantity of 3x plus 4, so two of the same binomials. And so we'll go ahead and distribute this 3x to 3x and the 3x to the positive 4. 3x times 3x is going to be 9x squared, and then 3x times positive 4 is going to be a positive 12x. And then we're going to go and use the 4 now, so 4 times 3x and 4 times 4. 4 times 3x is going to be another 12x, and then 4 times 4 is going to be 16. We have two identical middle terms here, so they're not going to cancel out, they will double. And this is that perfect square trinomial, so 12x and 12x are going to combine to make 24x plus 16. For number 12, this is not a perfect square trinomial, rather this is going to be a difference of squares. So we have 8x minus 3, and we have 8x plus 3. Hopefully you know right away that these will cancel out in the middle terms, but let's just go ahead and write it out so it makes a lot of sense. If we go ahead and distribute here, 8x times 8x is going to be 64x squared, and then this 8x times positive 3 is going to be a positive 24x. Following this negative 3 times positive 8x, then negative 3 times positive 3. So negative 3 times positive 8x is going to be a negative 24x. And a negative 3 times positive 3 is going to be a negative 9. Because we knew this was a difference of squares pattern, these are opposites and these will cancel out. And at the end, you will be left with a perfect square trinomial of 64x squared minus 9. For 13, let's check this one out. This one we have some higher exponents, so be careful with these ones. If we go ahead and expand this, we have the quantity of 3x squared plus 5y. So these patterns work for higher powers as well, times another of the same thing, 3x squared plus 5y. So again, we're squaring the whole thing, so we have two of these, okay? We're going to go ahead and distribute this 3x squared and multiply that by this 3x squared, and then multiply it by this 5y. So let's think here. 3 times 3 is 9, and then x squared times x squared is x to the 4th power. Remember, when they have the same base, you can add their exponents. So that will be 9x to the 4th power, and then 3x squared times 5y. So we have two variables here, but 3 times 5 is going to be 15. And then x squared times y is just x squared y. They just are next to each other through multiplication. In the middle, then let's go ahead and distribute this 5y to here and this 5y to here. So first 5y times 3x squared, well 5 times 3 is going to be another 15. And then you have this y times x squared, or alphabetically it's x squared y. And then finally 5y times 5y. 5 times 5 is 25, and then y times y is y squared. In the middle here, we have two identical terms, which should make sense because this is a perfect square trinomial, even though the exponents are higher. So this 9x to the 4th power stays the same. If you add their coefficients, 15 plus 15 is 30. Everything else stays the same, 30x squared y. And then we have this plus 25y squared that remains at the end. For number 14, let's take a look and see what we have. Looks like we have the quantity of 2x squared minus 3y squared multiplied by the quantity of 2x squared plus 3y squared. Okay, so they're very similar, but one's plus and one's minus, so this must be a difference of squares pattern. So I'm going to do this slowly here because there's a lot going on. First, we're going to say 2x squared times 2x squared. 2 times 2 is going to be 4, and x squared times x squared is x to the 4th power. Then we're going to say 2x squared multiplied by this 3y. So 2 times 3 is going to be 6. And then x squared times y squared is literally just x squared y squared. You don't have to do anything much with that. Moving on to this negative 3y squared multiplied by this positive 2x squared. So if we do that, negative 3 times 2 is going to be a negative 6. And then y squared times x squared is the same thing as x squared times y squared. So I'm just going to keep it alphabetical. And then this negative 3y squared times this positive 3y squared. Negative 3 times positive 3 is negative 9. And then y squared times y squared is going to be y to the 4th power. Looking at the middle two terms, these are like terms and they are opposites, so they will combine to make 0. And you are left with a difference of squares of 4x to the 4th power minus 9y to the 4th power. Both of these final terms are perfect squares, and we are having a subtraction between them, so it is a difference of squares. Let's just go ahead and check out the last two now for 15 and 16. For 15, it looks like we have a perfect square trinomial pattern happening here because we have two of the same binomials. So we have 5x cubed minus 4y to the 5th power, but it looks like we have two of those. So we have another 5x cubed minus 4y to the 5th power. So we should end up with a trinomial here. So let's go ahead and distribute this 5x cubed to this 5x cubed. So 5 times 5 is 25. And then x cubed times x cubed. Remember, we can add those powers together. That's going to be x to the 6th power. Then 5x cubed multiplied by this negative 4y to the 5th. 5 times negative 4 is going to be negative 20. So it's negative 20 x to the 3rd power, y to the 5th power. Then we'll go ahead and use this negative 4y to the 5th and multiply it by 5x to the 3rd. So negative 4 times positive 5 is going to be negative 20. And then y to the 5th times y cubed is the same thing as y cubed times y to the 5th. Finally, this negative 4y to the 5th times this negative 4y to the 5th. Negative 4 times negative 4 is going to be positive 16. So we can write positive 16. And then y to the 5th times y to the 5th becomes y to the 10th power. In the middle, we have two like terms. They have the same identical variable parts, but they have the same leading coefficients in front of them as well. So they will combine and double. So we have 25x to the 6th power. Negative 20 and negative 20 make negative 40. We have x cubed y to the 5th power. And then we have a plus 16 y to the 10th power at the end. Finally, for number 16, in this last one, we have a difference of squares pattern. So we have the quantity of 3x to the 4th power minus 8y to the 3rd power multiplied by the same thing, but we have an addition between these this time. So that's how we know it's a difference of squares. So what we're going to do here is distribute this 3x to the 4th power to this first term. So 3 times 3 is going to be 9. And then x to the 4th times x to the 4th is going to be x to the 8th power. Then we take this 3x to the 4th power and then multiply it by this 8y cubed. So 3 times 8 is going to be 24. And then the x to the 4th power times y to the 3rd power just stays as x to the 4th, y to the 3rd. Then we're going to go on to this negative 8y cubed and multiply by this 3x to the 4th power. So negative 8 times positive 3 is going to be a negative 24. Then y cubed times x to the 4th is the same thing as x to the 4th times y cubed. So that ends that term. And then this negative 8y cubed times this positive 8y cubed, well, negative 8 times positive 8 is going to be negative 64. And then y cubed times y cubed is going to be y to the 6th power. In the middle, notice these two terms, they are opposites, so they will cancel each other out. And just like we thought in the beginning, this is a difference of squares. The perfect square is 9x to the 8th power. That's a perfect square since the square root of it is 3x to the 4th power. And then we have this minus 64y to the 6th power, which is also a perfect square because the square root of it is 8y to the 3rd power. So there you have 16 different practice problems where we were multiplying special case polynomials. And the two special cases we were looking at were difference of squares, where you have two binomials where one has a plus, one has a minus, but everything else is the same. And then we also had the perfect square trinomials, where that means you have two binomials that are identical to each other that multiply to get a perfect square trinomial. Again, there are many types of polynomials you can multiply out there, but these are just two special cases and you're going to see these patterns a lot, so just try to get used to them. So that just about wraps up this video. Thanks for stopping by and sticking to the end. Hopefully you found it helpful, and as always, keep up the great work, and I'll see you in the next one.